Okay.
So go whenever you're ready.
Sure. Okay.
All right, so we're happy to start off Friday with our second 2 lectures from Lehner about gravitational waves.
Okay, so as I mentioned yesterday, today I wanted to talk about some things that are a bit more out there, but there were things that we did not cover yesterday, so I'll just mention briefly some of those, because I think there are some very cute things that be good to just at least exemplify. There is, however, some questions that some of you asked me afterwards, which I think are very relevant. So remember what I said. Okay, there is a puzzle here, a possible puzzle, not a puzzle yet, but it's a possible puzzle of LIGO haven't seen things so far with low spin. So there's an interesting idea, which again likely is too out there for the moment, and we may very well be wrong. That maybe there is another interaction that is depleting the spin of the black holes. But remember, we had these ones in X-ray studies. Many of those have spin. So that's an interesting puzzle. So if you invoke some interaction with some matter field and scatter field to deplete the spins of these black holes, then you have to answer why these guys do have spins, or many of those do. Of course, they can fix it with using the mass of the action in the right way. These guys are safe. Another interesting consequence of that model is that LIGO would have an gravitational wave emitted by the action cloud as it relaxes, and that is rather monochromatic, and LIGO is searching for it. So sooner or later, we're going to either vindicate that idea or just throw it away, which is great. So yesterday we were discussing maybe some of these events that could happen if you have the merger of 2 neutron stars, of black hole and neutron star. And I want to kind of tie again with what I started the discussion yesterday with, which was this idea that we should be able to explain eventually how these systems, the short gamma ray bursts, actually work. And the leading model is that they need something like what we see here. So a black hole hyper-accreting from a surrounding material. And this is what powers the main burst. If that's it, yes?
Sorry, I have to.
Hey, Paul, how are you doing?
So basically, neutron star mechanics, I think about the harmonic basically push the down to the star and hit each non-flow. Is something like that?
No, so black holes have a viscosity. That's an interesting question. Let me get back to it but please remind me, because it is very interesting. So the black holes have a viscosity, and that's very clear evidence in the gravitational waves we see. And the fact that they are, in a sense, have a very strong viscosity, effective viscosity, already rules out many putative alternative models for compact objects. But no, they don't have these kind of instabilities, but you guys, you'll see, have pointed the way to some other instabilities that are not the same, but once you actually take seriously the nonlinear nature of the equations, many more things can happen. So yes, if you have this event or this stage of very high accretion on the black hole, you have no problem in explaining the burst. But remember, I said there are other scales in the problem. Some subsystems or some subset of the short gamma ray bursts emit for a very long time afterwards. Well, how do you accommodate that? Or some have a strong emission even before the burst itself. Again, how do you accommodate that? The reason we keep looking, or people kept looking at the black hole at hyperaccreting, is because that's something we knew. We knew how black holes, single black holes, accrete, and this was kind of the leading toy model that astrophysicists had to look around and try to accommodate for observations. I'll show you a few other examples as we go along, that once you have access to how the dynamics of the system behaves in a more complete way, then you begin to identify other instances in the system where you can have a very strong emission. Still, we don't know, we cannot explain yet these other scales in the problem, but that's a work in progress. So I showed this yesterday, so I'm going to go quick. I'm just going to spend maybe 15 minutes on this, and then I'll move on to the talk I wanted to give today. So imagine now rather than doing 2 black holes or a black hole into a star, we start with 2 objects that do not have a horizon. So we send 2 neutron stars. Imagine this having gone on for a very long time. The waveforms are exactly the same as 2 black holes of the same masses, because remember, the tidal effects, the matter effects, only show up at in this post-Newtonian expansion as v over c to the 10th power. So it's a very puny number. It makes absolutely no influence whatsoever unless they get sufficiently close. And the reason is because the tidal effects come with this m over r to the 10th power, or multiplied by something. Multiplied by something that is a radius of star divided by the mass to the 5th power. So that if you have large radius, then this number could be huge, multiplying a very small number, and the combination could actually play something interesting. So here is just a scenario where you have these 2 neutron stars coming together. They're going to smash against each other at what speed? At around 0.3 times the speed of light. So imagine you're taking 2 objects with the mass of the sun, but just cramped in 15 kilometers, and you smash each other at a very large fraction of the speed of light. You're going to generate this massive neutron star or hypermassive neutron star, depending on how much mass you had at to begin with. There are tidal tails, tidal effects that send the whole amount of material out. I'm going to come back to it, but just to give you some sense of numbers, about maybe 0.01% to 0.1% of solar mass gets thrown away. This is very nuclear-rich material. It will undergo a series of nuclear processes. You're going to form a whole bunch of heavier elements. Among these, about 2 to 3 times the mass of Earth in gold. So if you're looking for funding sources, that's one of them. And it will come with a very clear counterpart that we can go after. We discussed yesterday about the waveforms. The waveforms are obviously very different for us. It tells us about the equation of state. These are 3 different possible equation of state, 3 different mass ratios. And the fact that they are very clearly different at some stage tell us that eventually we're going to be able to tell them apart with gravitational wave detections. And I said yesterday the task per signal is very difficult because the differences are very subtle. They arise very much towards the end of the sensitivity noise curve of LIGO. So LIGO is just ramp up this way. So right when things get interesting from this point of view, LIGO starts to get deaf. But eventually there'll be things that will replace LIGO, will be much better. If you're interested, I can tell you some of the plans that there are. But at this point, statistics can do a lot. So if you have a whole bunch of events, you can begin to tell them apart. And then you have a lot of very clear differences when LIGO really becomes very bad. But that's when you can, if you identify particular features of the behavior of the system, you can combine different observations to dig this even further from the noise. And this is, if you have looked at some of the techniques that astronomers use, is used all the time. It sometimes comes under the wording stacking. So if you have one signal and you happen to think that another event is of the same, you can put one on top of each other and keep doing this till the picture becomes sharper. For that, again, we need a lot more theoretical information to be able to tell this event and those events are the same. We can combine. And I'll give you an example later on about that. Just on the context of timescale or this possible other source of interesting emission, it says, imagine if you smash 2 neutron stars. Imagine each neutron star has, or one of them has some amount of magnetization. We believe there will be of the order 10 to the 8 Gauss, 10 to the 9 Gauss. But now you ask how much energy is in the magnetic field of the star as compared to the binding energy and the collisional energy of the system, and it's essentially nothing. So if the magnetic energy is able to, or the magnetic field is able to tap a tiny, tiny amount of the kinetic energy that was involved in the collision, it can be ramped up to a very high value. And numerical simulations have shown that you can start with 10 to the 8 Gauss, you smash these 2 against each other, and then you end up with 10 to the 17 Gauss. That's ridiculous. We've gone up by 10 to the 16 sort of magnitude. Now imagine that object collapses into a black hole, and we know by the known-Hare theorems that they have to shed off all the extra crap. Well, that amount of energy is huge. In fact, it's about the same amount of energy you need to explain the gamma ray burst. 10 to the 51 ergs come out if that happens. So this one possibility that the burst is precisely that. It's this massive neutron star that is collapsing to a black hole. There will be a black hole with material outside. That will be accreting. And this is an easy way to explain the main burst and the very long sustained emission. So that's one possible way of explaining the first figure I showed at the very beginning of yesterday's talk. But we don't know. We're still exploring everything. So the most exciting thing about gravitational wave astronomy is not just gravitational waves, it's everything that you could do with it. In particular, the buzzword is multi-messenger. So try to get as much information from the universe, from everything you can get your hands on. And that's gravitational waves, electromagnetic waves, and if it happens close enough, you can get neutrinos from it. And so the communities, both on the astrophysics front and on the gravitational wave front, that very actively investigating what are the most promising channels to get detect multiple detections, or detections from multiple bands. So I'm not going to go into everything. I debated with myself to really changing the slides to just shorten the amount of information. Actually, I'm going to skip several slides just to give you the information in case you want to look at the things afterwards. So there is here I talk about two different cases. One, if you have two neutron stars coming together, each one with its own magnetosphere. Once they interact so strongly, even before the merger takes place, that you essentially will have a pulsar on steroids, something that will just shine for a short period of time very brightly. And this is one, it's forward-looking, but when LIGO told you, look here, it's about to merge in the next couple of minutes, you can go and dig it deeper with telescopes. That's one. And the other one is this one, and the reason I like this one is related to the comment I made before. Imagine things are too dirty for us. The engine is this messy neutron star, or massive neutron star, lots of material around. So let's be safe. Let's just go far from the system and concentrate on the amount of matter that was ejected. This amount of matter I said, or the order of 0.1% of solar masses, and then ask what, if any, could be related on the electromagnetic side with the decay of these elements. So this is this pulsar on steroids thing. And then let me just talk about, yes, this plot. So when you look at the relative abundance of elements out there, and also on Earth, you ask, how did we make, or how nature made these heavy nuclei, or heavy atomic mass numbers? The leading model has been supernovas. So a supernova goes off, sends a whole bunch of material, which again is neutron-rich, and nuclear processes take over. They produce many of them very radioactive elements, and when these elements decay, there is something that we know is a clear signal you can go after. But it has always been a puzzle of what happens at the very high mass number. So it seems that supernovas had a hard time making them. Why? It's because of this thing. There is something called the electron fraction. So this is how, if you want neutron-rich or electron-poor, the material is. And there was some magic number. If this YE happened to be smaller than 0.2, you had no problem making the very high mass numbers. If this number is higher than that, then you really hit some particular band limit on the nuclear processes, and you don't make them. But of course, we go and measure them. And so then the question is there a better arena to produce the material with the right properties? And the fact that I mentioned this is because the answer would be yes, and it's binary neutron star mergers. You can actually look at the simulations, compute what is YE number is, and what the characteristics, the amount of material and the velocity is for binary star mergers, and ask the question, are there any case for perhaps changing the equational state that fulfills the right properties? And the answer is yes. If you have a neutron star with an equational state that has, for a given mass, a smaller radii, the collision is so much more violent, you send much more material out. That material gets out very cold, so it doesn't have time or tries to get to a beta equilibrium, and you have very clearly very small values of Y. That doesn't happen if the neutron stars that merge had an equational state that caused them to have a larger radii. So the difference on that is important, because the opacity of this material changes in a significant way, depending on where you actually go to the very high lanthanides and the very high atomic mass number elements or not. And as a result, you either have a counterpart that is peaking the infrared or the ultraviolet. So imagine LIGO, sometime in the future, sees a binary star. You take all your telescopes, you point in the near infrared, the ultraviolet, and you see a signal in one case or another. That gives one example of this additional information that now comes from electromagnetic origin, and gives you enough information to build a case towards perhaps one equation of state versus another one. This is it's a very cool idea. And then just to wrap up, let me just mention this. I'm a very big fan of this paper that came out 2 years ago. I really recommend you reading it, because it's one of the things you can go read in the spare time. It's a short paper in Nature. The author list is already impressive. It involves a whole bunch of people. One of them works in nuclear waste management, and the other one is an astrophysicist. And I'll tell you what they did. They just went to the bottom of the ocean, and they picked some chunk of rock, and they measured the relative abundance of 244 plutonium. The lifetime of 244 plutonium is too short to have been part that amount measured to have been assembled or put there by the time Earth was formed. So it had to come from outside, or be made by us by some nuclear experiments. You can estimate 3 cases or 2 cases. Supernovas, we know. Let's say supernovas, and every theory we have is wrong as to saying that supernovas may not be able to go and produce these very heavy elements. Let's assume they do. We see supernovas. A supernova goes 1 every second. So if you want to count Mississippis, you can be, or sound geeker, you can just say 1 supernova, 2 supernova, to just count seconds instead of Mississippis. So we have a lot of supernova productions or events, and you can estimate, based on the rate of supernovas in the galaxies, how much of that material should have been obtained. And the measurement is about 1,000 times less. Then you say, well, but some of the folks have been playing around with nuclear bombs. How much would us produce? And that's also 1,000 times much lower than observed. So supernovas would have given you 1,000 times more than observed. Earth or human events would have given you 1,000 times less. Then you're somewhere in the middle. And then you say, well, what is our current understanding of binary neutron star mergers rates? How much would they have put out? How much you expect to see? And it gives you something that's perfectly consistent with what has been observed. So this is a beautiful thing. And as I said, if you look at that, there is so much physics in 4 pages. It's one of those things that when I read it, I said, oh, this is the reason why I got to do physics. So let me just stop here and let's switch gears. We're going to go crazy now. We're going to say things that may actually be wrong, but I think it's some of the things that we're beginning to have opportunities to think about how to be wrong, even thanks to gravitational wave detection. So first, let me just tell you, there are some slides that if we have time, we're going to get back to it. In case you're interested in numerical relativity, there are some slides that tell you a little bit about formulations, sources of information. There is even an online course if you want to take a look at, but I'm not going to go there. I just perhaps just show that. Usually, people in theory would cringe at doing numerical simulation, because if you're smart enough, why would you use a computer? I think that's a very wrong attitude, because if you actually find the right calculation that you cannot do with pencil and paper, but that can apply you through some important consequence, you may actually find that you obtain new and unexpected things to think about, where now you can go back to your pencil and paper. But aside from that, let me move on. As I said yesterday, I'm not someone that loves computer. I use them when I have to. I love this one. If you read this book by John P. Boyd, gives you the definition of an idiot. You can bring fears into people doing numerics if you ask, have you done the test that he said? And then if he says no, if the speaker says no, then you can just point to the definition. You might not want to do that. Then there is something about the compositions, which I'm not going to get into. Again, so this is where we are. So we'll see how we go in time, and maybe we'll come back to that. So let me just start with a prologue, and we're going to build from there on. So we have had the theory of relativity for a little bit more than 100 years. And arguably, it's an incredibly successful theory. But if you actually go and look at the history of it, there was a lot of confusion, even up to the 60s, where even wondering themselves where gravitational waves were real. There's this very famous meeting where Bondi came and said, well, gravitational waves are real, and you can heat your tea with it. There is also this is the very same meeting where Feynman came and left disgusted. I'm not sure if you've seen that quote. It's actually beautiful. He basically writes to someone and says, remind me never to come back to general relativity talks or conferences. I would be very happy to talk with him today. But they are very interesting. Very limited solutions were obtained because the systems of equations are very complicated. But even those limited solutions are playing a key role in astrophysical applications. Oops. They're trying to explain these objects where you have jets. In this case, the length of a jet structure is much longer than the length or the typical scale of the galaxy, where whatever putative system is producing these jets. We believe they are produced by these black holes accreting, etc. So even with our limited knowledge, a lot of we have been able to exploit it in interesting ways in astrophysics application. And so much so that gravity has leaped from the theory into Hollywood. You might think that I'm going to bring up Interstellar. I'm not. I'm going to bring this. I'm not sure if you have seen this movie. You probably haven't. If you haven't, stayed that way. So this is a picture where it's called The Expendables 2. There's a whole bunch of people. He's going to write Einstein's equations. He's going to write it correctly. He even was going to use the G over C to the 4th power. But he's going to tell you what he thinks of the theory in a second. Because I think he's a quantum gravity guy. Okay, there it is. Unfortunately, he just call it the special theory of relativity. But if you saw Rocky IV, Sylvester Stallone punched him quite badly, so maybe that's a consequence of that. Anyway, so where is the theory today, and what do we know, and how much do you think we can push on it? Well, depending on which side of the camp you are, you might say, well, maybe we already know that GR is breaking because of things like dark energy and dark matter. And if you haven't talked with people on that camp, they're convinced that because of this, we already know or have strong reasons to think about what replaces it. I think that's a valid argument. I'm not in that camp, but that's definitely a valid argument for it. But I'm more on the other side. Okay, we have amazing data, and we're going to have even more. How we can go about testing it. And for that, as I said yesterday, we need to know what the theory has in store and how much we can push and think of clever ways of pressure testing it. And the next few decades, in my mind, will be likely dominated by understanding dynamical solutions, because everything we've been able to obtain, or most things that we've been able to think from geometrical, general arguments, we probably have exhausted much of what we could do. So let me just start. And slowly I'm going to be diverging to the crackpot path, but I think it's an interesting thing to consider. So first I'm going to just tell you some of the things we know and love about the theory, and then slowly challenge it in different ways. So as I said yesterday, we picture black holes are simple objects, at least in 4 dimensions. They are bold, and we think we understand very well their linear response, i.e., if you perturb a black hole, how it will bring down to equilibrium. From a mathematical point of view, we do not yet have a full definite proof that black holes are stable, because there is a kind of an annoying corner that needs to be proved. But by and large, for what a physicist would like to see, we know they are stable. Stable in the sense that if you kick a black hole, you end up with a black hole. But I'm going to argue that there are 2 different notions of stability. One is, if you have a black hole, you kick it, you end up with another black hole. The other one is, if you kick a black hole and you analyze it at a linear level, would it behave the same way as if you kick a black hole and you analyze it at a nonlinear level? So mathematicians would call this linearly stable solutions, i.e., the solution to the linearized problem agrees with the solution to the nonlinear problem linearized. And I'm going to argue that the answer is no. And I'll tell you how. For that, we're going to just take a detour and then try to get intuition from a different camp and then come back and see what the consequences are. So just to remind you, because this is going to be important, when you do black hole perturbation theories, I mean, if you've ever done perturbations, you know absolutely is the case that whatever your perturbation scheme is, might be very good, very efficient at picking up some particular feature of the solution, but it actually might not be very convenient for other features. In the standard perturbation wave theory for black hole, you say the black hole metric, G, let's say, is given by some background, plus a collection of different terms, H1, H2, H3, etc., which each one being subleading with respect to the previous one. There might be phenomena where that approach is not necessarily the cleanest, most efficient way to capture, and I'll tell you one example, which is crucial. But with this approach, we understood that the perturbations are described by something called the quasi-normal modes that have both real and imaginary parts, so there's something that oscillates and decay. The decay has to do with the fact that energy is being lost into the horizon and out to infinity. If there were no energy lost, we would have just normal modes, and we would have just the oscillation part. Just for context, I'm going to remind you of something that was actually started in the 80s by Thibaut Damour and then carried much farther by Keith Thorne, Price, and McDonald. It was this thing that the equations of motions of general relativity are so complicated, where we do have very little intuition to grab onto, to try to understand what to expect. So back in the 80s, this gentleman tried to say, well, can we map the solutions or the behavior of Einstein's equations into something else we are more familiar with, i.e. electrodynamics or hydrodynamics. And this thing called the membrane paradigm, where you imagine the black hole surrounded by a slight membrane, and then you try to see how that membrane would behave as seen by Einstein's equations, then gave a lot of interesting insights onto how the theory may behave. But it was very ill-defined, so we always cringe a little bit as to any answer he gave you, because you could tell, well, what if I choose a different membrane? Would the difference with the arguments and consequences change? This was resurrected later on in the context of fluid gravity correspondence, and I'm going to get there, and we have one of the persons responsible for it at the back of the room. So I said yesterday about this. This was prior to the detection picture from Kip Thorne. Of course, he was trying to sell the effort to the rest of the community. He said, well, anything can happen in the middle, right where the merger happens. We're going to need supercomputers to resolve this. And then this is reality. On the theory front, once we solve it, and then we know with actual detections, the same thing happens, where the transition is very smooth. So how do we explain that? Already at the theory front, when the first waveforms were produced, people said, how is it that it's so simple? There is, I mean, it's not that Kip was just making this up. It's a rather clear possibility that you have a lot of messy things in between. Completely a posteriori, with 20/20 hindsight, then this is the answer that is given. Well, maybe you actually are generating all this extra structure, but nature provides the common event horizon that hides it away from an asymptotic observer. So they are all just hidden away from us. That probably may very well be the case, but if that's so, black holes are tremendously powerful. Not only do they hide the singularities from us, but they also hide all the extra nonlinear features. So if this was a tax cheater program, it's amazing. And the first thing you want to know when you find out is cheating taxes, and not how much you want to punish that person, is how did he do it? And so that's what we want to know. And I'm going to try to argue that maybe we have an argument for it. So, okay. So I'm not going to go there. So let me just mention a few things. So we want to pressure test general relativity, kind of perhaps challenge some of the preconceptions, and see what we can do with it. So the very first thing is just, I'll give you an example of why is it it's very important to know explicitly, very accurately what to expect. So one option is, I'm going to give you something that is very, very simple. You would think that people who have thought about this much earlier, because we have examples in astronomy, the stacking example, but I'll tell you what it is. The punchline that we want to measure more than one mode of decay from a black hole is because measuring one mode already constrains the theory. If you measure, well, one mode tells you where it's consistent with the theory. If you measure a second mode, you actually stress test the theory, because the measurement of one tells you what to expect from the next one. And papers have been written to say that even unless LIGO is extremely lucky, we're not going to be able to go after the second mode. We are going to get the first mode, the fundamental mode. LIGO has already gotten them. Just to put things in perspective, LIGO's first detection, remember I said that a requirement for LIGO to say something is real is that signal-to-noise ratio has to be 8 or above. The first detection was so loud and with the right masses that the signal-to-noise ratio of the decaying part, if you forget about all the inspiraling, is already 7 or 8. So just that itself would have been good enough to almost detect the signal. But with that very loud object, you say, well, how much SNR do I have in the subleading mode? And that's essentially nothing. So you cannot go after it. And the conclusion is we need more money to build the next detector. So maybe this is making us a little bit unpopular, but we're saying, wait a minute, you may not have to. You still have to buy the next detector. It's a pretty cool thing to have. But we can do the following. So we know from what I said before that each individual mode, at least in the regimes where this linear scaling is applies, is fully determined by the solution. So if I understand what initial parameters of the source are, and you tell me what will be the relative amplitudes of different modes once the merger is happening, I know precisely what to give. General relativity tells us everything. So if we start with the premise that we're going to test general relativity, you build a Bayesian analysis and say, okay, this is how we start, and we just anything that it implies has to be accounted for the data. So now suppose you have a whole bunch of data, a collection of events that have different parameters and everything, but we know precisely what these omegas that I wrote before are. So this is now the real part and the imaginary part are called gamma. Different masses will have different values, different spins will have different values, but we know precisely what those values are. So you can do something very simple where you say, well, let's stack the signals. So different events will have all these guys differently, but let's say you measure the first fundamental mode that you have, because it's something that is very easy to detect with the gravitational wave detector. But then you're allowed to play this game. You take each individual event and you target the next mode. Say you want to see the 3-3 mode. So in a spherical harmonic composition, this is a L equal 3, M equal 3 mode. So I pick any one event that you care, and define this as the special frequency and the special phase. And then take every other single event that you have and rescale it. So if I rescale the time by the weighted factor of the ratio of the frequency of my preferred mode and the 3-3 frequency, the 3-3 value that the other event should have, then you can begin to combine the signals these ways. You add them up. And once you do this, what you have is a signal that has a whole bunch of omega 2-2 modes, but all resonating with the same omega 3-3. And once you put them together, you can dig this out. So our prediction is that within 1 year of LIGO's observation, at the rate of detection that it has, we're going to be able to dig the next mode. So it will be very soon the possibility where we actually put this very, very strong pressure test, the theory. Yes? It's arbitrary. That's an excellent question, and there is not a unique answer. We can differ on that. You can say, well, given the peak of the waveform, you can start saying that's your t equals 0, or it's slightly afterwards. But regardless of our independent definitions, we can do this, except that now your phase will be, if you say t equals 0 is there, well, I say t equals 0 is over here, our phases will be slightly different. But that's the only thing we need to account. But the fact that you know the individual masses from the earlier in spiral you could say, well, if you choose a t equals 0 that is really different from mine, the relative amplitudes will be different. The relative phases will be different, but we will be doing the same kind of calculation. You're going to be subtracting by a little bit more than I do. But still is the case that the later ring down will be having a coherent stacking of the frequencies. You do, yeah, so you have to do the Bayesian analysis and the likelihood. Absolutely, you have to go through all that. It's small, yeah, it's small. So it's fundamentally dominated by the uncertainty of the determination of the individual parameters. And so if you were doing everything exactly, you would accumulate events as square root of n. If you were doing everything incoherently, it would be n to the 1/4. So you can ask, well, what is the penalty you're paying? So it's less than square root of n, but it's much better than n to the 1/4. So if you expect it's in the log scale, this kind of slope, this slope is slightly lower than that, but you can still say, well, at what point will I have built up enough SNR to say this mode is here with this value? And that you need of the order of 40 events with an SNR of 12, or sorry, yeah, of 10. And with that, then you can make that, you can definitely say what the whether that 3-3 mode is consistent with general relativity or not. Because if it's not there, then you're already saying, oh, the theory, the underlying theory is not respecting the values we expect from general relativity. So if you account for the number of events a LIGO will have in a given year at the rate it's measuring now, assuming it will get to design sensitivity, you're going to have of the order of 100 binary black hole events. Then you ask how many of those would have the criteria that the first mode is very clearly visible. That's a subset of maybe 40, and then those are enough to dig this hard one. Yes. Yeah, when we can do the analysis already in the signal. So remember, the LIGO has already done this exercise for the first fundamental mode. And so then there is a very reasonable window that after the main peak of gravitational waves where you say, well, this is where I already contrast a linear thing. And in fact, this is how the templates have been built. So as to give that to LIGO, they do a kind of a smooth matching between the Erlin spiral, the merger from numerical relativity that is kind of enhanced in the effective one-body way, and then you match to this linear expectation. So the good thing is that the detection has already informed us what the best practice model is. It's not an order of magnitude smaller, but it is significantly smaller. Exactly.
Can I understand physically what these modes mean and the fundamental mode basically having something to do with the angular frequency or something?
Yeah, so
some modes are, are they related to the masses or what?
So they're all mass and spin related. And this is just a response. So if you imagine your black hole having some particle that is falling into the black hole, let's say, there is some structure on an effective potential, and the possible resonances within that potential is essentially giving you what these different frequencies are. But they are all uniquely determined. If you give the mass and the spin, I know all of them.
Did you show the formula for black hole?
No, I haven't. So there is a fit that I have somewhere, not here, in the previous, and the other slide I do have that, so I can show it to you afterwards. So, but that's in the context of what if things are not like we expect in GR? What do? Now we're in trouble because we would like to not just know that GR is not correct, but in which directions should we be looking for a replacement? And here is where the rubber hits the road. If you actually want to have answers from the nonlinear regime of the theory, you better have a theory that makes sense in the nonlinear regime. And I'm going to claim in the most positive and humble and well-intended way that most theories out there do not satisfy this properly. They are not they do not lend themselves in mathematical terms to what is called a well-posed initial boundary value problem. If you do not have that, then there is nothing you can do. I'm sorry. And that's a problem, because in cosmology, or from quantum gravity arguments, or effective field theory arguments, people have written all sorts of theories, which are extremely well motivated. But from the point of view of, can I ask nonlinear questions to that theory? The answer is not really. You have to find ways to fix some of the problems that those theories have, and I'll allude to some of these and then the plan. If you then say as a criteria, I want to only work with the ones that are well-posed, that do themselves allowed to well-posed initial boundary problems, there aren't that many. There are the scalar tensor theories, scalar vector tensor theories that usually have, like the Ricci scalar, so the Einstein part, maybe with some weighting conformal dilaton there, which if you go to the Einstein frame, it's gone. It just gives you some coupling with a particular scalar field, maybe with some gauge fields, etc. But beyond that, you don't have many more. If you ask how much difference you have, it's not a lot. Yeah, sorry.
What's the age?
Oh, this is, if you want, this is the magnetic field. This is an electric component, this is magnetic. So if you dualize it, so you can write, this is a 3 tensor. I can write it as another 1 tensor. So it's, yeah, it's a 3-4. And this is a theory that comes naturally derivable from, or as a limit of string theory, one limit of string theory. If you ask how much difference do they make, well, if you study matter, study scenarios with matter, they can make a huge difference. Very clearly differing. I'm not going to go into the details of these, but it's just how different values of the coupling introduce very strong variations in the gravitational wave. And that's because the stars now acquire an extra charge, which is called a scalar charge. And that scalar charge induces a renormalization of the Newton constant and possible dipole radiation. So that has significant impact on the dynamics. We actually see binary neutron stars. We can do this test. But again, this only happens at high frequencies, and that brings an interesting conundrum. We could see the differences in the gravitational waveforms, and then we still are going to have to answer the question, is a difference arising because of difference in the equation of state, or arising because of difference in the theory of underlying theory of gravity? And that also requires as much information as we can, both from gravitational wave input and electromagnetic. And if you want, I can go and describe some of these. Then, if you apply one of these with black holes, the scalar tensor theory does not give the black hole any extra charge. You need a vector, you need a gauge field, at least. That does give you some interesting phenomena. Unfortunately, that phenomena is governed or is proportional to the charge that the black hole, either if it is a real charge or it's a charge or there's some extra gauge field that is not coupled to the standard model. But if you don't believe that that charge will be high, then the waveforms are essentially all the same. So this is our waveforms for the value of the coupling going from 1 to, say, 3,000, and you can barely see this difference. LIGO will have a very hard time detecting those. So if those are the theories, are representatives of the theories that might replace general relativity, we're going to be under a very difficult task of trying to discern general relativity from any of these. Of course, the opportunity would be on the systems that involve at least 1 neutron star where the difference would be higher. But as I argue, I don't think we're going to have many events in the very near future. So what else can we do? Well, ask the question, what else might be there? And in particular, where we have learned enough of general relativity to really be sure about what to expect. So now, and in particular, as I argued before, we don't have a lot of intuition as to what the nonlinear nature of the theory is, and numerical simulations coupled with new kind of insights are beginning to tell us what to look for. But it's always interesting to look for new lampposts to see where else we might find some ways to gain intuition. And so for that, I'm going to just really take a detour. I'm going to go on the ADS CFT front. Do you have a question? Yes. No, I agree with you. I mean, if anything, it will correct it. So I have two different issues. So on the physical, if we think on the physical point from the physical point of view, the coefficient should be small. Any effects will be very, very subleading. But eventually, we have a very powerful detector, many events. Maybe we can hope to go get something. And the alternative is we don't have anything else. This is the strongest nonlinear gravitating regime that we can get our hands on. We should look. That's. No, now I'm going to tell you. So now if I put my mathematical hat, I have a problem. Regardless of how small these correcting terms are, they have pathologies. And I'll give you an example in just a second. And those pathologies means, from the mathematical point of view, are completely uncontrolled. Typically, a physicist would do the following. Say, oh, that's fine. I don't care. Those are small. I can go and fix them. I'm going to make just reduction of order. There are all sort of buzzwords that you can invoke to do this. And if you were doing this problem analytically, maybe, and I would argue against it, but maybe you have a way, you could see a way to control these terms. But I would argue that you don't have a way. But regardless of that, the problem is at the end of the day, you're going to put this in a computer. And the computer will excite all possible frequencies, even the ones that you don't think should have any physical input to. And because of the structure of the equations, unless you do something with it, they just blow up. Yes, absolutely. Absolutely. But let me get back to this. Is precisely what I'm trying to get after, because I'm going to argue that something like that might very naturally happen. And then if you try to fix it, maybe you're messing up with the physics. But I want to say that perhaps everything is fine, but only perhaps. So we're going to take a page of ADS-CFT. I mean, you all know about or have heard, and you're going to learn more during the course, so let me not go into this. But one cool thing that I'm going to get my hands on is that, motivated by ADS-CFT, people went looking for a duality between gravity and anti-de Sitter and relativistic hydrodynamics, and Paul's name is going to come very soon. But I'm going to tell you just a few things, because this actually opened some interesting possibilities. If you actually know or look at when this duality actually is supposed to realize, so gravity in the bulk of ADS, dual to some relativistic hydrodynamics in the boundary, and you ask, what are the scales when that happens with respect to physical problems? That's the same, it satisfies the conditions for turbulence. And this is the first time I heard about this, and I said, there has to be something wrong somewhere. Because people typically did not expect turbulence happening in gravity. Because this will say, well, we know hydrodynamics here will account for the turbulent regime. So then there has to be a dual gravitational turbulence. And people have said this in some context is nonsense. And so let me just tell you what the arguments were. So people saying that the gravity could not go turbulent is to say, well, we know perturbation theory, we know cosine-mosal decay, we don't have anything that is growing exponentially, at least for some time, so something is, that is nonsense. Numerical simulations were colliding black holes, and these numerical simulations have this ability to refine themselves whenever finer features arise. And we don't see them self-refining to death. So what's going on? And I swear this argument I have heard people say, we know hydrodynamics has shocks, and we know for a fact that general relativity does not have shocks. Hydrodynamics typically have turbulence, therefore GR shouldn't have turbulence. Of course, that doesn't follow logically, but it was used. Of course, the ADS-CFTers know better, always by definition. That's a joke. This thing is there because we have ADS-CFT. That's a rule of life. An ADS hydro is obtained, motivated by it. At the end of the day, even if ADS-CFT is wrong, the duality was found to be there. And also remember in the Riemann paradigm, you already knew that there was a connection between hydrodynamics and general relativity. So me being agnostic about everything, I said, well, there is a win-win situation for me. Because either I'm going to show there is something odd about the ADS side, or there is something new about the gravity side. So let me just get a piece of this action. And hopefully we can reconcile a whole bunch of things. So first I need to say, well, if we're going to go looking for turbulence, we need to agree on what turbulence is. Because people usually would say, well, I know there is turbulence if I see it. There is an analogy with something else, but let me not go there. But actually, I'm gonna argue against that. If I just plaque on this water pitcher there, I'm gonna argue that there might be turbulence in there, even though you don't see it. Anytime you have nonlinear features, kind of combining to actually change the behavior you expected from a linearized analysis of the problem, when nonlinearities can do something interesting, I would argue that you have some features of turbulence, even though they might be short-lived for any useful or interesting thing to happen. So let me just list a whole bunch of things that I would say, well, if we see these things, we're going to call turbulence. So if it breaks symmetry, if you see some exponential growth, albeit maybe very small, this is non-linearly stable argument. If the global norm of the solution, in the case that you don't drive it, you don't keep putting energy, has an exponential decay followed by a power law with another exponential decay afterwards. And if you see an energy cascade, then I would say I would call this turbulence perhaps in a more general, nice way. But the thing that I really care here is that we know, at least for Navier-Stokes, that when you plaque a system described by Navier-Stokes and not in the turbulent regime, there is a direct energy cascade. So all the energy wants to go to shorter and shorter wavelengths. In two spatial dimensions, you have both inverse and direct. But more importantly, most of it goes inversely, goes to longer wavelength. There is little, comparatively speaking, going directly. And this is no coincidence that we have the analog of the Millennium Prize with respect to solutions, global solutions to the nonlinear problem of the Navier-Stokes problem, solved for a two-dimensional spatial case, but $1 million is waiting for someone that can solve the three-dimensional case. And so everything is connected on that front. So just one, and apologies to Paul, because I'm sure Paul will give a much better presentation. Just this is kind of the GR regurgitated way of presenting the fluid gravity correspondence. So remember, I showed you what the typical perturbation scheme in general relativity is. You say that gravity is, the metric is your background metric plus the addition of correcting terms. What these folks did, of course, taking a page of what they know is the best way of using to analyze the dynamics in the hydrodynamic front, is they just change that scheme. Imagine that your metric is given by your metric, the background metric, except that now promote every single constant that you had there to a function. And your perturbative scheme is going to impose that gradients are subleading. So derivative of order n is smaller than derivative of order n minus 1. And then you're going to put that into Einstein's equation and see what you get. Once you do that, and then you do suitable projections on the ADS boundary, the analog of the momentum constraint and the Hamiltonian constraint basically tells you that there is a symmetric tensor that has 0 trace and 0 divergence. If you then begin to do suitable identifications, this implies that what you have is that SAB happens. You can write it in terms of now a TAB. I only changed the S to a T, but you can identify each individual component of that tensor, and it will give you a relativistic hydrodynamics. And they worked out all the way to second order. So you recover at 0th order the Petrov fluid, at the next order shear viscosity, and the next order also agree with what you expected from relativistic hydrodynamic discussions say that you would find in Landau-Lifshitz. So now this is a fact. I have to live with it. And so then I can ask questions. We knew, or I argue that we can, in 2+1 dimensions, you decay mainly inversely. On the gravitational front, remember, you build up one dimension. So it says in 3+1 dimension, maybe gravitational wave perturbations will actually decay inversely for the most part. But that happens because there is another quantity in 2+1 dimensions that is called Enstrophy, which is a very weird name. But it's the fact that that object changes at a rate that is much slower than anything else implies in 2 dimensions that you actually cascade mainly inversely. And you don't have that luxury in higher dimensions. And so the first thing we did was just to check that the hydrodynamics of the right regime goes turbulent, and that's one example. It's a simulation that shows that it shows a vorticity, some initial profile goes turbulent, and you actually begin to see that As time goes by, you get longer, they cascade to longer wavelengths. So it's clear that these features have shorter wavelengths than those one, and then you keep going. Let me not go here. If you don't believe that, this is what gravity should be doing. You can actually go and do a full numerical simulation of 3+1 gravity in ADS, and this is what Paul Chesler, Alan Adams, and Hong Liu did very soon after. This is a bona fide generativity simulation in 3+1 gravity, and you can see the features. Of course, they cannot match one-to-one because there is chaos essentially going on, but the fact that you have very much the same features gives very strong evidence that this is indeed going on. I can show you what happens if you do the analog or the dual of Kerr. Remember, you cannot put a single patch to cover the sphere, so numerically what we have is 6 patches. So this is the North Pole, that's the South Pole, and then 4 patches going around the equator. And if you do the same calculation, you ask what is vorticity doing. With time, let me just show you only the bottom case. That's a case that is dual to a Kerr, so it has some given rotation. You form all sort of vortices. Color tells you where it's co-rotating or counter-rotating. Eventually, they begin to merge, and you end up with 2. One at the North Pole, one at the South Pole. And beautifully, you actually see that if I ask you what is a multipolar decomposition of these blobs, you're going to say, well, I don't know in L. There is a whole bunch of L's. But in M, there is only one. M equal 1. It's just doing this. We're going to get back to this. So we have to be very careful if we're going to call there is turbulence in gravity, because a cat has 4 legs, but so has a table. And I better not confuse the two. So modulo, just not pushing the analogy way too far, I should be able to see what else can I get. There is a whole bunch of things that we know on the turbulence side in hydrodynamics. For instance, there is very interesting correlation in the stress energy tensor. And there is quantitative difference between the behavior in 2+1 dimensions versus the 3+1 dimensions. So in 3+1 dimensions, this correlation scales linearly with the separation between points. In 2+1 dimensions, you have, depending on the scales, you have the opposite sign or a different power. But then after we kind of were convinced that something in gravity is very much related, what the hell is this implying on the metric tensor and why? This is something we have never thought or pondered, and it's something we should go after. Let me not, the virtue of time, not say more about this, because I really want to get to the end. There is very interesting possibilities, depending on which camp you're in. You may be on the camp that really wants to understand better hydrodynamics and turbulence. So, okay, then there is a way to perhaps use gravity to bring new lights into the problem, or vice versa. You want to understand new things in gravity, so you use the intuition from gravity of hydro to look for new things. And I'll show you one example of this. But of course, we shouldn't get carried away. This was a very special case. We were doing things in anti-de Sitter. In anti-de Sitter, you only lose energy into the black holes. You're not losing energy through infinity. So maybe you would say, well, this duality between gravity and hydro, it's only really valid if you're in ADS. If I use my PDE, mathematical hat, I find that very strange, because ADS just adds something that's called a lower order term. It's lambda GABs. It doesn't have anything. It's a linear term. There is no derivative of it. We're very strange. So physically what it's doing is to put a cap on how much energy I'm losing, and therefore it's reducing the rate at which the decay happens. But that's interesting from a nonlinear point of view, because if that's the role of ADS, it says whenever I have a linear perturbation that lasts long enough for nonlinearity to do something interesting, maybe the theory will do something interesting. So this is what we did with Huang Yang and Aaron Zimmerman. Is say, well, let's just look for a case in asymptotic flat spacetime. So we're not going to cheat. We're not going to put things in ADS. And then let's see if the same thing happens. If one ingredient was that the linear decay mode should be very slow, we know a very clear case where that happens. Take a black hole, make it highly spinning. The higher the spin, the lower the decay rate. And let's analyze there the behavior of the system. First, let's just remember parametric oscillators. So if you have an oscillator described by this equation, where there is a function, there's a time-dependent function here in the undifferentiated term, you know you're going to have all solutions, most solutions will decay exponentially given with the rate of decay given by gamma, but some, that whenever this function is in an, say, oscillate with a 2-to-1 frequency with respect to the natural frequency of the oscillator, you're going to have an exponential blow up at this order. So let's see if this happens in gravity itself. And the answer is yes. So how do we do it? Well, we do a typical linearized analysis of the problem, but we want to go to next order. So first, you imagine your solution is Kerr plus some given mode. And now you say, well, how will an additional mode behave in the background, not given by the Kerr solution, but the time-dependent space-time given by the Kerr plus the perturbation. And if you go through the calculation, you find that a parametric instability is allowed by the equations. And I'm not going to go into the details, but this is basically what you do. You find out that this new mode obeys an equation of motion that is like this. So it's a wave equation for a Kerr space-time plus some operator that depends on time because of the background mode. And then you're going to have a solution of the form with an exponential growth, and the exponential growth rate is given by this. And of course, the growth rate is going to be the largest. If this term is the largest possible and that term is the smallest possible, this again where you see the 2-to-1 relation of frequencies, that is a requirement. And whenever this happens, okay, you're going to have the blow up at this order, of course. So what does this mean? Oops. You can analyze the requirements for the instability to take place. And essentially what it says is every time the size of your perturbation divided by the azimuthal number divided the natural decay rate of that mode is large, you're going to have an exponential blow up. And the larger it is, the faster it's going to be. And now you can use your duality and say, well, the size of the perturbation, let's call it velocity, 1 over the azimuthal number, let's call it wavelength, and this is a decay rate, that's like viscosity over density. If you do that replacement, you recover that this is nothing but the fluid Reynolds number that you have called for to understand fluid turbulence. So bottom line is, in the right regime, gravity, general relativity itself, has this behavior. If you ask, remember this 2-to-1 relation of frequencies, what is it implying on the structure of the mode? It implies that if you have energy in mode M, it wants to transfer that energy to mode M divided by 2. So if you start with an L equal 2, M equal 4, ultimately you're going to end up with an M equal 1. And this is what we saw before in that simulation, end up with these two blobs that are going in the north and south pole. So if Gargantua actually really existed and LIGO were to see gravitational waves from it, what is it you see? You'll see at the end of the day not an L2, M2 mode decay, which is what we're seeing so far, but actually most of the energy will go in the M equal 1 mode. And LIGO should be prepared to look into that. And this is one example that I bring as to maybe if we actually did not know about this, we go and detect the waveforms and we see something odd, we would have said, well, maybe GR is incorrect. When what was incorrect was our understanding of the nonlinear features of the theory. Let me just, not go into the details of this, but let me just mention what is possible. So we did the calculation at a very high spin for convenience. But if you ask, suppose you have two objects going around, how will the size of the perturbation on the space-time itself scale with this parameter that knew how close to extremity you were, that's this kappa to the p? And Strominger, Hadar, and Porphyriadis did the calculation, and they found out that the size of the perturbation is of the same scales with kappa in the same way as the omega. So to leading order, you could simplify that and say, well, to leading order, it doesn't seem to be so sensitive with the spin. So we did the calculation at the very high spin regime, because that was the case where we can do it most cleanly. But perhaps this is generic. It's not just for the very high spin, but generically, this nonlinearities actually primarily want to push energy back. If that's true, and I'm just postulating, if that's true, then we can explain this without calling for the event horizon to really hide everything. we can just say you have these objects that are coming together. They're continuously driving the system with an L2, M2 mode. That energy nonlinearists might want to naively push things and create finer structure, but because of this inverse cascade, it's pushing things backwards to stay in the L2, M2 mode, because that's the main one that we're driving with. This is a bit out there. It's very provocative, but maybe it's correct. And I think now that we have seen gravitational waves, whatever nature is doing, it really doesn't seem to be wanting in these regimes to actually put a lot of features in the small scale wavelengths, because we don't see them explicitly. So I'm going to get now to the question that Dan was asking me about. So there is a lot of possible connections of these and a lot more that we have to look into. In particular, if we ask what really drove most of the energy going in the opposite way in fluid dynamics, was the existence of this quasi-conserved quantity that is called Enstrophy. So this is pointing the way to perhaps there is such a quantity in general relativity and we have yet to identify it. And postdoc at PI, Stephen Green, is actually working on that. So there is a lot here. So just for fun, before I go in the very last topic, I will show you something. Remember, some of the things that happen, there's a lot that happens once you buy the fact that gravity can go turbulent. In particular, you can have a fractal structure. And if you haven't seen a fractal structure with black holes, let me show you one. This is a black string. There's a black hole in 5 dimensions. There is an extra dimension going that way. We started with a perturbation. It just put most energy on 2 bulbs and generated a very thin string. That string is itself unstable, and this process keeps going and going and going. And so this is the ultimate fate of the so-called Gregor-Laflamme instability. You're going to end up having necks that shrink themselves to 0 size and reveal a naked singularity. Because this is 5 dimensions, but definitely you can see a fractal structure here, and this is a fractal structure of the horizon itself. If you haven't seen this before, you can actually do this experiment. So this is a very beautiful movie. This is human saliva. Sometimes you have to get creative, I guess, if you don't have enough funding. And I'm not going to describe this. Anyway, so this is, luckily for us, we still have some time for before lunch. But then you can ask where and what else could this have implications? And this, let me go now exactly to where Daniel's question was. So most of these effective field theories derived from whatever sort of very interesting motivations are, have a structure of this form, where you have Einstein's equation plus some extra piece that is supposed to be small. And you're supposed to use it where it's small. You should be in cases where the wavelength is sufficiently long, where this is just a very, very minor correction. But if you actually then put this thing in, and then you analyze what structure mathematically you have this, you have all sort of nonsense. You have acoustic propagation, blow up in arbitrarily finite time of solutions. So then what do we do? One option that people have been exploring is to say, well, maybe we have to do some clever reduction of order thing where you actually solve first GAB equal to 0, you find the solution, you plug that solution here to evaluate the right-hand side, you plug it, and then you solve it again, and then you solve it many times, and you see if you converge to something. That's something you can definitely do. Where you're going to get a sensible answer, that I don't know, a priori. And I can tell you why. But we have seen this problem before, and people have addressed this. And this is the so-called Israel Stewart formulation. So let me go back to relativistic hydrodynamics. Then again, Paul is an expert on this. But let me just illustrate all these things that we have been arguing about and exactly the kind of questions that Daniel was asking. Take relativistic hydrodynamics and truncate it at the perfect fluid side. Forget about everything else that comes after that. If you ask, what are the mathematical properties of that system, they're perfectly fine. Everything is well behaved. Yes, you might have shocks, but that's a kind of a nuisance. But as part of the well-posedness of the system, you're good. Now add the first viscous term, the shear viscosity term, and then everything goes to hell. You have acoustic propagation, you have a runaway of energy to short wavelengths, and so no matter what you do, energy here wants to go there, because already at the perfect fluid side, if you ask, what is the Kolmogorov spectrum telling you if you want, it tells you if you're applying in 3+1 dimension, it wants to go to shorter wavelengths, and it's going to encounter things where these things are going to be big. And this is what Daniel is saying. Then the conclusion is you shouldn't be using it there, because you have abandoned the regime of applicability of the theory. But if that's the case, then we are going to be able to obtain very limited information. But then you can approach this in two ways. One is to say, well, can we fix it in some way? And this is what Israel Stewart did. So there is a way to say, well, if you really wanted those extra terms to always be subleading, let's change the equations by fiat. I'm going to just brute forcefully, if you want. Actually, they did something smart. I don't want to be pejorative. But in a brute force way, you're going to say, I'm going to keep those terms small, and it's not difficult to do that. You can define everything else beyond the perfect fluid to be a new tensor, and you impose an equation to that new tensor to be such that as it evolves, it keeps the extra terms subleading. So now mathematically you're golden. Everything is fine. You have a well-posed theory, or you can define well-posed problems with this theory. But now you can say, well, have we messed up the physics so badly that we cannot really gain anything useful out of this approach? And I'm going to claim that if you remember these energy cascades, the answer is absolutely you can do things in 2+1 dimensions, in 3+1 dimensions and higher. It's a question mark. Oops. Oh, I'm missing a slide. I don't know what happened. But anyway, so I argue now you can do this and fix it mathematically. And if you're applying this theory in 2+1 dimensions, where energy wants to primarily cascade in the opposite direction towards longer wavelength, you're significantly not affecting, or you're not affecting the solution in any significant way. So now we can take a page of this and really take a leap of faith from what we've discussing before to address these kind of questions. If we're in 3+1 dimensions and we believe we drank from the Kool-Aid that really things are primarily cascading to longer wavelength, of which we have some partial evidence from theoretical analysis, and if you want strong evidence in some sense from the actual observations of gravitational waves, we can now have a program where we change this equation using essentially this Israel-Stewart formulation or idea. I will define a new tensor here. I will impose that it always stays subleading. I will apply it for 3+1 gravity, and there I should have sensible answers. If I want to use exactly the same scheme in 4+1 dimensions, I wouldn't trust what I'm getting. But only in 3+1 dimensions I can do that. Incidentally, remember I said the other technique where you actually solve the equation 1 without this term, you use the solution to plug it there and just iterate. The very same argument would have to be called for to make sense of that approach. So if it is true that energy primarily wants to go to longer wavelength, I think that approach would work as well. But we didn't know this a priori without this observation. Hopefully that answers my gut feeling. Again, I preface this with went on the cuckoo side, but I don't have any other way of understanding how to defend this approach better. With that, I think I'm done, unless you want to know something on numerical relativity. You have a question?
No, I just wanted to point out that there's potential about that we discover that you don't have to
I agree, but you have right. But I agree. If we were there, we can go in that route, and that work. That I am aware of that work, and it's very beautiful work. But in many theories, people only have a truncation to some degree. They don't even. I mean, it's not clear what comes afterwards. I mean, and it depends. There are so many theories. That what I said about at least at this very basic order. If you're going to try to get the first answers, maybe you can go pick your favorite theory because everyone will have one, and then just follow this program. This may be a way to address that and begin to say these are the consequences once you go into this direction. I think it's 75 minutes, or if I have. more time, I can go. But okay, then I'm done. Thank you. Agree. And yeah, so I'm going to answer, I think, with the sociological answer. So one thing, and I'm going to fully quote you on this. I've been actually saying LIGO has now gained the right to be wrong, and they should exercise that right. But before that, they were extremely worried. And so if anything, LIGO has been absolutely ultra-conservative for historical reasons, and I'm sure you know some of that. But I think they should grow out of it. And I agree with you. They should be, so the post-Newtonian, just so that everyone knows, if you write the post-Newtonian scheme, there are terms that are very well known in general relativity. And then you ask the question, so and these numbers are fixed by something that general relativity tells you. Then you can go to the data and say, what is the likelihood of those numbers being something else? And then they see if they pile up on the GR value, and then they add some other terms. And those other terms have not been very exploratory. They've just done the simplest possible way. But I think this is a dialogue that needs to happen. And these are the questions I wanted to start asking you about. On the extensions of the alternative to GR, I think there's a dialogue that needs to happen to actually inform, because this is a community that for a long time has been, by necessity, very conservative. But now is the time to just explore anything. Maybe 5 years from now, everything is so constrained that it wouldn't be the case that we should be doing that. But absolutely, and this dialogue has to happen. It hasn't happened. Yeah, absolutely. I agree with you. Yeah. I mean, in some sense, maybe what it turns out that once you write it that way, you can actually map the answers you want to what they're already doing, but that mapping hasn't been thought through.
Something that I think you didn't come back to. You said something about linear stability of solutions.
Oh, right. So I didn't come back.